This fact, got it. And due to this fact, many of the standard tools that have been developed to study interacting particle systems cannot be useful here. So we have to resort to new tools. Okay, so short overview of the first lecture. I've tried to be very soft today. I wanted to give an introduction, hopefully at the level of everybody who even doesn't know anything about interacting particle systems. I'll start by presenting our first model, which is called the Fredriksson-Anderson two-spin facilitated model, or for friends FA2F. Then I give you more examples and the general definition of kinetically constrained models. I will come back to motivations from physics, so to what is this liquid glass transition and why these models can be useful to study it. And then I will introduce a very much related deterministic dynamics, which you might already know, even if you haven't yet heard about KCSM, which is Bootstrap Percolation. Then we will discuss ergodicity and mixing for these models. We will discuss the time scales, how to quantify time scales, so the study of the relaxation time or its inverse, which is the spectral gap, the study of the mean infection time. We will see what it is. And I hope I'll have time to discuss at least one proof today, introducing one of the first tool that we will need to study these models, which is what we call a bisection constraint technique. Okay. Okay, so and then in the second lecture, I'm trying to give an overview of the week. We study more in detail the behavior of two models, which are two paradigmatic kinetically constrained models, to keystones to build this theory, which are the East model and the Fredriksson-Anderson one-spin facilitated models. And then I will discuss what happens. I will discuss universality results for these models in 2 dimensions. So essentially what happens when we change the constraints which tell us which moves are allowed. Then in the third and fourth lecture, depending on how long I took for the previous subject, I want to discuss a more recent result, a sharp threshold for the first model that I will introduce today, the Fredriksson-Anderson two-spin facilitated models. And I hope I will have a lot of time also to discuss the out-of-equilibrium dynamics for these models, because there is where there are most open issues. So let's get started with the first model. So the Fredriksson-Anderson two-spin facilitated model. So we are on the integer lattice, in the Euclidean lattice, ZD. And on each side of the lattice, there is either a particle, so the site is occupied, or the site is empty. So this is the configuration space, 0, 1 to the ZD. The dynamics for this model is a Markov process of Glauber type. Namely, it's the dynamic of birth and death of particles. Sites which are empty can get occupied, and sites that are occupied can get empty. And to define the model, I have first to fix a parameter, Q, which is a parameter which is in the interval 0, 1. Then the dynamics goes as follows. On each side of the lattice, I have an exponential clock of mean time 1. Clocks on different sides are independent. When the clock rings on a given site, then the configuration, the occupation variable at that site can be updated. In particular, what happens is that, first of all, I have to check whether the site has in the current configuration at least 2 empty nearest neighbors. If this is the case, then I update the configuration on that site, and I update it to empty at rate Q. Q is my parameter, which I had fixed before, and I update it to occupied at rate 1 minus Q. Otherwise, meaning if the site on which the clock rings has not at least 2 empty nearest neighbors, the update does not occur, and I go to the next clock ring. So this is the dynamics. We'll come to a formal definition in a second. So this model is characterized by the presence of a kinetic constraints, which is this having at least 2 empty sites, empty nearest neighbors, in order to be able to update. For example, here I depicted the configuration. and I made a red square around the site here, which has the constraint which is not satisfied in the current configuration, which means that if the clock rings on this site, no update can occur. The sites with the green circle is instead a site in which the constraint is satisfied because I have 2 empty nearest neighbors. And so if the clock rings here, I throw away the current occupation variable and I replace it with 1 at rate 1 minus q and with q at rate with 0 at rate q. This is the dynamics of this Fredrickson-Anderson two-spin facilitated model. And you see that what enters, there are 2 things that enter to define the dynamics. Q, the parameter, which defines the probability to reset to empty a site whenever it can be, its occupation variable can be updated. And the other thing is the constraint, which tells me to update, I need to have at least 2 nearest neighbors. So I can change this constraint, and if I change this constraint, I can have access to all the class of kinetically constrained models. So I'm going to, before giving a formal general definition, I want to give you some zoology, the names of the most popular models in this class. And it's not just to make a zoology, but because we will see in the course of the lectures that the different choices of constraints that I'm proposing here give rise to a completely different, qualitatively different behavior. Okay, so first of all, the model that is called FAJF. I guess you already guessed what it is. If FA2F was the model in which I needed 2 empty neighbors in order to update, FAJF is the model in which there is a parameter J, I need at least J empty nearest neighbors, in J empty sites in the first neighbors. Then there is the East model. The East model is a model in which I require at least 1 empty site in the oriented neighborhood, which is formed by the sites which are near the site on which the clock rings in the positive direction.
Ben oui. Puis en plus, sais-tu, si j'ai regardé moi, je me suis dit après le 14.
Somebody speaking on. Okay, so then there is the Northeast model. The Northeast model is a 2-dimensional model. Okay, one can extend it to higher dimension, but for the sake of this course, we'll just consider it in 2 dimensions. It's a model in which, as the name says, in order to perform the move, we require the neighbor to the north, so x plus e2, and the neighbor to the east to be empty. Okay, then sorry for this long list, but we will be rewarded by the fact that all these models have different behavior. In a second, I will show you. Then there is the Duarte model. The Duarte model, again in 2 dimensions, is a model in which we require at least 2 empty neighbors in the neighborhood, which is formed by the neighbor to the north, to the south, and to the west. So above me, below me, and to my left. And finally, there is the spiral model, which is a model in which, in order to update, I go and look at 4 types of neighborhood. These are sort of L-shaped neighborhoods around the site in which I want to update. There will be a drawing in 2 slides, in which I look at the 4 neighbors, which form my neighbors to the northeast and to the southeast, and I require all of them to be empty. Drawing in a second. And if this is not the case, I want at least one of the other 3 possible sets obtained by 90-degree rotations to be empty. Okay, the drawing is coming just after. So after giving you the general definition. So what is the general class of model to which we are interested? What is a KCM in general? How has the constraint have to be in order for a model to enter in the class of the models which we call like that, and we will be able to deal with? So first of all, we have to define the constraint, and to define the constraint, we have to define what is called an update family. The update family is a set of neighborhood of the origin, which has to be finite, as you might suspect. So I will be dealing with the constraints which are of finite range. The set of this neighborhood is also finite. So I have a finite set, a finite collection of neighborhood of the origin. And furthermore, these sets in this update family do not have to contain the origin. Okay. Then the constraint if I fix one such family of sets, the constraint corresponding to this choice of the family is defined as follows. I say that the constraint is satisfied at a given site X if and only if at least one of the translated at X of these neighbors of the origin is completely empty. Okay, this is a general way to rephrase the constraints. And then the dynamics is defined for once this update family is chosen, and once the parameter Q, which enters in the point tosses that define the update is chosen, the dynamics is defined as for the FA to F model, saying that each site updates to empty at rate Q and to occupied at rate 1 minus Q, provided the constraint is satisfied. So this is a way to rephrase in a general framework the constraints. And you see that the model in which you require at least J empty neighbors corresponds to the choice of the update family, which contains all the sets that have at least J neighbors of the origin. So I want at least one of them of these sets to be empty. The East model, the model in which I want to have at least one empty site in the positively oriented neighborhood, corresponds to the choice in which the update family contains all the neighbors of the origin in the positive direction. The Northeast model corresponds to the case in which I have update family which contains the neighbor to the north and the neighbor to the east, both of them, and to the right, both of them should be empty, and so on and so forth. Then you can see that the last two models can be rephrased by this choice of the update family. Okay, in the case of the Duarte model, I want at least two empty neighbors in the north, south, and to the left, and so these are the three possible sets in the three sets in the update family. One of them should be empty, at least one of them. Okay, in order to perform the move. Okay, so what is a common feature of all these models? A common feature is that due to the fact that the constraint never looks at the configuration on the to be updated site, and this comes from the fact that the update family U does not contain the origin. You see in the general definition, I wrote in red an important fact, the fact that not only this, I should have a finite collection of these update sets in the family that determine whether the constraint is satisfied. Not only they should have finite range, but they should not contain the origin, so that when I want to check if the constraint is satisfied, I don't look at the configuration of the origin. Okay, thanks to this fact, as we will see more explicitly in a second when I define the generator of the Markov process, thanks to this fact that this dynamics is reversible with respect to the Bernoulli product measure. And it is the Bernoulli product measure which I indicate with mu q, or simply mu in the following, which is the measure which gives weight 1 minus q to the occupied sites and q to the empty sites. So the parameter q is the density of empty sites in this equilibrium measure. And this corresponds, this is the same thing as saying that the dynamics is reversible with respect to a Gibbs measure which has no interaction. So it's simply, the Hamiltonian is simply the sum of the occupation variables. And if we want to make the link between the inverse temperature and the density parameter of the empty sites, this is the formula. So the density of empty sites is inversely proportional to exponential of beta. Okay. A second common feature coming from the, so this first feature might go in the direction of saying, but these are very trivial models. So the models are not trivial, but luckily the equilibrium measure is product, so it's a trivial equilibrium measure. And in fact, it was the dynamics was chosen in purpose in order to have a trivial equilibrium measure. We'll see in a second why. The second comment is that the dynamics of this KCM is not attractive in the sense that, in the sense of interacting particle system, in the sense that which roughly corresponds to saying that if I have a configuration and then I modify it by injecting more vacancies, more empty sites, the presence of more empty sites can have unpredictable consequences, in the sense that it does not necessarily goes in the direction of helping me empty more empty sites, because having more empty sites means that I have more sites on which the constraint is satisfied, and this in principle can also mean that I can fill more sites, because once the constraint is satisfied, I can either fill or empty. Okay, so this is as a consequence tools like which are often used for other Glauber dynamics, for example, to study the dynamics of the Glauber-Ising model, like cannot be used here. In particular, tools that involve coupling are usually not very efficient here. In particular, it's not possible to couple two initial configurations, one of which contains more empty sites than the other, in order that this order is preserved at later time. Another observation is that we cannot use here argument that use the censoring. Censoring, for those who are not expert here, this level just for me means that I won't be able to use arguments that use the fact that I froze a part of the system to a certain configuration and I let the rest evolve and hope to say that my real dynamics without freezing goes at least as fast as this one. Because freezing means that I freeze the certain constraints, and this can have, as I said, unpredictable consequences. Can go in the direction at certain moment of filling more sites or empty more sites. Okay, so another observation is that I said that the Bernoulli product measure is a reversible measure for the process, so it's an invariant measure, but it's not the unique invariant measure. And in fact, this is again a consequence of the constraints, which imply the fact that due to the presence of the constraints, there are configurations that are blocked under dynamics, and also measures which are concentrated on this configuration or on or different superposition of these blocked configurations are also invariant. And so as a consequence, we will have to deal with some ergodicity issues with the presence of several invariant measures, and also with the fact that it's not possible for this model to have a relaxation which is uniform to this equilibrium measure, to this Bernoulli measure on all initial conditions. For example, if I start from a configuration, say for the FA2F model, which is for any of the models that I said, which is completely filled, none of the constraint is satisfied, and so this configuration cannot evolve. So a measure which is concentrated in the completely filled configuration for all the constraints that I gave, it's an invariant measure. But there are also less trivial invariant measure, which comes from the fact that depending on the constraints, I can have different blocked configurations. For example, for the FA2F model, the model in which I require at least two empty neighbors, if I have a configuration which has a, say in the infinite volume, which has a double line, a double row, one after the other, which is completely filled, none of the sites in this double row will be ever empty to be, able to empty, because each of these sites has at least 3 occupied neighbors all the time because of the double infinite occupied bar. So for sure, a configuration which contains this cluster will have this cluster at any later time. So there are also configurations which contains subset of the configuration which are blocked. So and some ergodicity issues. Another key property is that, which is a trivial observation, is that due to the fact that in order to update, we have to have at least a certain number of, or at least a certain neighborhood which is empty. And with respect to the equilibrium measure, empty sites have a density Q. The dynamics will, in general, slow down when we choose this external parameter, which defines the model to be smaller. So Q going to 0 corresponds to inverse temperature going to infinity in this Gibbs measure rephrasing. Okay, so as I said in the beginning, due to this peculiar feature, so to the presence of these constraints, which are hard in the sense that the presence of these constraints implies that some of the update rates can be 0 depending on the constraints. Several tools have to be profoundly modified in order to deal with these models. Okay, then again for the common features, so I wanted to discuss a little bit more the motivation coming from physics. As I said, the models were introduced in the 80s. The first one to be introduced was FA2F model, if I'm not wrong, but by Fredriksson and Andersen. And they were introduced to try to understand the liquid glass transition, which is still nowadays a major open problem in condensed matter physics. So what is the liquid glass transition? I'm referring here the glasses, even the glasses of our windows. So it's the following, roughly is the following phenomenon. If I take a mixture of silica and sodium carbonate at sufficiently high temperature, so I raise the temperature. This is in a liquid phase. And then if I cool the temperature, cool the system very abruptly, and go beyond the temperature at which this liquid would turn into an ordered solid, the liquid does not have time to create an ordered structure inside. Essentially what happens is that if I cool sufficiently fast the liquid, the liquid enters into a regime which is called of super cool liquids. It remains a liquid. It's not able to organize itself in an ordered crystal and solid structure. It remains a liquid, but its time scales, which can be measuring viscosity of the liquid, increase dramatically, in the sense that depending on the liquid mixture, by just changing the temperature of a few degrees can change the time scales of the order of 14 order of magnitudes, 10 to the 14th. So so the liquids, the dynamics of the liquid slows down very abruptly until essentially the liquid is so viscous that it can no more flow, and the liquid gets frozen into a solid state, solid in the sense that it cannot anymore flow, but not solid in the sense that it's ordered. So if we look at the microscope, the liquid that has frozen into a solid state, the state of glass, its structure remains amorphous. So the structure of the glass is essentially undistinguishable from the structure of the liquid if I look at the microscope. So it's an amorphous, disordered solid. So the key point here, the feature is that on the one hand, we have a sharp divergence of time scales, but this time scales, this sharp divergence is not accompanied by a significant structural change. So it's not due in particular to the fact that there is a structural long range order which is created. And just to cite two sentences, one from Phil Anderson, who wrote in Science in '95. Phil Anderson is a Nobel Prize in condensed matter physics, I think in '77. He wrote, so now more 20 years ago, or that in his opinion, the deepest and most interesting unsolved problem in solid state theory is the determining the theory of the nature of glass and of the glass transition. And he also predicted that this could be the breakthrough for the coming decade. It has not been a breakthrough in the coming decade. Physicists still strongly disagree on the mechanism which underlies this phenomenon. A theory of the liquid glass transition is still far beyond our reach. And this is in the words of Giorgio Parisi, who is a Nobel Prize last year. And he has very much studied the complex systems, disordered systems, and in particular the liquid glass transition. So, and just to, before coming back to math, just to motivate you a little bit more. So it's not just an academic curiosity, understanding the behavior of the glass, because the glass is a material which is very present in our daily life. Men have been manufacturing glass since 2000 years. Though we still don't understand the theory very much. So it's a material which is, if you think just a second, is a material which is widespread, and due to the fact that it's hard, it's inert, so we can put inside the liquids and they are not contaminated, they are not modified, it's transparent. This feature is very much technologically important. We can shape it when it's hot as we want, and it's also very fashionable because it's sustainable, so it's fully recyclable. And that's because I wanted to say something which I discovered thanks to Evaluar Tastic this morning, is that 2022 has been proclaimed by the United Nations the International Year of Glass, due to the fact that the glasses are playing a very major role in every types of science and technology, in particular in communication. Just think of optic fibers. And some people are claiming that now it's time for the age of glass nowadays. So 2022 is a year in which there are many conferences, etc., art, architecture, etc., for this value of the glass. But anyway, from the theory, from the point of view of a physicist, which besides the technology, one very intriguing thing is that a dynamical arrest towards an amorphous solid is a behavior which is shared by a large variety of materials, very different from the supercooled liquids which undergo the liquid glass transition. In general, these transitions are called jamming transitions, and they occur in a larger variety of materials like granular media, polymers, colloidal suspension, foams, emulsions, varying an external parameter, which in general is not the temperature, but perhaps the density of the way we vibrate a granular. We can have some these transitions which are very similar in behavior to the liquid glass transition. So understanding one is of key importance. So now, which is the connection with our, to go back to math, which is the connection with the kinetically constrained models. The point is that the idea was that introducing these kinetic constraints, which the particles should satisfy, the sites should satisfy in order to update their variable, should mimic what is called the cage effect. The cage effect, very roughly, is the fact that if I have a liquid and I am at low temperature, so at high density, molecules can prevent the motion of other molecules. So if I want to move, I have to wait that, the idea is that I have to wait that the cage formed by the neighbors is opened in order to move. So the idea is that behind the introduction of this model is that the big increase of time scale, which gives rise to the liquid glass transition, could be due to the fact that there are locus constraints. The constraints are not of infinite range, are very local, but these local constraints can create a frustration which induces the presence of large blocked structure, which is inducing this divergence of time scales and hence the glass transition. So that's why, as I said, it was made on purpose, choosing models which have a trivial equilibrium. So an equilibrium measure, the Bernoulli product measure, which has no static interaction. Physicists could very well have chosen different models with the kinetic constraints plus some local interactions, but the idea was really to try to be as simple as possible, to introduce a toy model which has nothing in its equilibrium, nothing strange that occurs by varying the density, and yet, due to the presence of the local constraints, could show some behavior which is reminiscent of the liquid glass transition. And in fact, the reason why this model continued to be studied is that numerical simulations immediately show that these models, for properly chosen, for proper choices of the constraints, display a divergence of time scales when the density of empty sites is decreased, which is very reminiscent of the experimental data. They display aging, so memory effects. So out of equilibrium, they display behavior which depend on the history. They display dynamical heterogeneities, namely essentially the coexistence of fast and slow regions. So all phenomenology which is goes under the name of glassy dynamics and which is shared by the supercooled liquids. Now that we have a our motivation behind. I explained the motivation. I want to also to tell you which are the key issues. So also from a physical point of view, but which will be also the key issues that we will analyze. The first key question is how do timescale diverge when I said that when I decrease the external parameter which controls the equilibrium density of empty sites, the timescales increase. How do they increase? And how does this depend on the choice, on the specific choice of the constraints? Is it possible to find sort of universal behaviors, to classify the constraints in different classes to know their behavior? And a remark that I wanted to make is that in many cases, or for most choice of the constraints, numerical simulation are not able to give clear-cut answers, despite the big size of the computers. And in fact, several of the conjectures that were put forward using only simulations were wrong, because in fact, these models, the interesting choices of the constraints are such that the dynamics is very slow and the finite size effects are very important. So one really have to know the scalings before fitting the data. So this is the moral. Okay, so in order to give you an idea of the fact that this scaling is strongly dependent on the choice of the constraint, I have here written the scaling when the density of empty sites goes to 0 for a quantity which is one of the best quantity to quantify the time scales for the equilibrium process, which is started from the equilibrium measure, which is the first time at which a given site, say the origin, is emptied, what I call tau 0, so or infection time, depending on the which is the same, is the first time at which the origin is emptied. So let's just scroll the list. For the model, which requires at least one empty site in 2 dimensions, I just reported the results in 2 dimensions. In the 2 dimensions, the scaling is 1/q squared, the modulo log corrections. For the East model, the case in which I require one empty site, but in the positive direction, the scaling is already very different. So it's not the power law scaling, but it's a sharper divergence, 1/q to the power log q. For the model in which I require 2 empty neighbors, so Fa2F, the scaling of the infection time under the equilibrium process is exponential of the inverse of the density of empty sites. For the Duarte model, I jump here, it's exponential of the inverse of the squared density of empty sites. And for the northeastern spiral model, when I go to 0, this is the scaling when q goes to 0, is infinite, the infection time, the mean value of this infection time. So just, we will see, this was just to motivate you. At the end of the week, I will have certainly had the time to discuss all this behavior, to explain you how comes that there are these very different behavior, which is the mechanism which is behind all these different scalings. But just to say, in the case of the northeastern spiral model, this divergence, the fact that the infection times is infinite at 0 density, is due to the fact that there is a critical density, a positive critical density, below which blocked structures of particles, this blocked structure like the one of the double bar for the Fa2F, percolate. So there are structures that are forever blocked under the dynamics and which percolate. So if the origin belongs to one of these structures, it can never be emptied, hence the infinite infection time. For the East and then for the Fa2F model, the dominant relaxation mechanism when Q goes to 0 is dominated by the motion of single empty sites. But while for the Fa1F model, this motion is essentially a sort of random walk-like, and the empty sites are a distance, a power of 1/q, depending on the dimension, which gives rise to this power law behavior. Instead, for the East model, we will see that the entities which dominate relaxation are again the empty sites, but they cannot move freely, sort of random walk-like. But in order to move to cover a large distance, they will have to go through a logarithmic energy barrier, logarithmic in the distance that they have to overcome. And since the distance of zeros is with respect to the equilibrium density, this case as power law, so we'll have a 1/q to the log q coming from this logarithmic energy barrier in the distance. Then instead for the FA2F and for the Duarte model, the motion will be even more complex. It's a motion in which the relaxation is not driven by single empty sites. Single empty sites can do nothing, cannot move in any way. In order to relax, what will have to the key objects that dominate the relaxation are some sort of large and rare region. How rare? For both models, the probability of this, the density of this region scales as an inverse of exponential of 1/q. And then the motion of these large rare regions is very different for the two models. Hence the fact that despite this, the density of these regions scales in the same way, the scaling of the infection time is very different, so much sharper for Duarte model, in which instead of having the inverse of the density in the exponential, we have the inverse of the density squared, density of empty sites. Sorry. But this was just to suscitate your curiosity. We will see all these both from a heuristic and from a mathematical point of view in the next days. So what's next? Next is some notation. I really wanted to keep things basic and clear, so I like to introduce first some notation. So, okay, what I call omega is the configuration space for this model, so 0, 1 to the ZD. I will call by the Greek letters eta, sigma, the configurations. And given a configuration, I call for a given site, I call eta x the occupation variable at the site. Then, okay, same notation, but with the lambda index means that I'm restricting everything to a volume lambda. As I said already, I will indicate with mu the product measure with density 1 minus q. I usually drop the index q because it's too much, and you will see that all these scalings depend on q, which is the parameter which defines this law and defines the dynamics. Same with the index lambda when we are restricting to a finite volume lambda. And the only thing to which I want to draw your attention is that sometimes even for functions that are defined in the whole configuration space, say in ZD, I will consider the restricted mean. I will call mu lambda of a function f, which is defined in the whole configuration space, the restricted mean of the function f over the variables in the box lambda, with all the other variables held fixed. So it's a function of what this mean is a function of what happens outside the volume lambda. Okay, analogous definition for the variance, which is just the variance restricted on the box, so it depends on everything outside. So we will need, for what I'll do in the following, to have a clear idea of how the process is constructed. And for this, I'm going to go rapidly through the graphical construction of this model, just to settle the key variables, though I guess that most of you know it very well. So in order to construct the Markov process corresponding to what I informally defined as a model, so I have exponential clocks on each side, etc., what we do is that on each side of for each side of the lattice, we define a sequence of IID exponential variables of mean 1, those that I call S, X, K. X is the site, K is the index over this family. And I also define a family of Bernoulli variables, so 0, 1 variables, which have probability 1 minus q, with probability 1 minus q are 1, and 0 with probability q. So these are what I call the coin tosses. And then the times at which the clock rings that I was referring to before corresponds to, for each given site, the kth time at which the site, the clock at site x rings correspond to the sum up to k of these IAD exponential variables. And this form a Poisson point set on 0 infinity of intensity dt, the T-Lebesgue measure. So then to construct properly the process, say we are in finite volume, first of all. So say we are looking at a volume which is finite. Then if we fix a time, we can consider the union over all the sides of this finite volume of these clock rings, almost surely with respect to the distribution of this variable. This set is finite, and all the clock rings occur at different times, so we can order them in increasing order. And then what I'm left with to have the graphical construction is to define an operator, a map for each site, actually two maps. One map is a map in which takes the configuration for site X. I define a map Bx0, which take the configuration, the current configuration, and spits out a new configuration, which is the same at all sites except of X, where the site is set to 0. Same for the other map, Bx1 is the map which takes a configuration and it fills site X. Okay, if it was already filled, it gives the same configuration. If it's not filled, it gives a configuration in which I modify just site X by filling it. Okay. So now that we have this, that we are equipped with these random variables, we can proceed to the graphical construction as follows. So first of all, I want to define, I need to define a variable, a function, sorry, which depends on the, since we are on finite volume, I have to, and the constraint is looking around each given site, I will have to define a configuration on the boundary of my volume. So I fix a configuration omega outside my volume lambda, and I define a function Cx omega, which is a function which is 1 if the constraint is satisfied at site X for the configuration sigma with boundary condition omega, and is 0 otherwise. So so if I consider, for example, FA2F model on a square, and outside I have fully occupied configuration, and I'm sitting at a site near the boundary, this function is 1 only if that site has in the interior at least 2 empty nearest neighbors, since in the boundary condition there are none. I can, once I have fixed this, the family of coin tosses, so the variable that define the coin tosses at each given site, and the Poisson clocks, I define the process iteratively as follows. So the process started from a configuration eta. So I give a configuration eta in my volume, and I define iteratively the process with boundary condition omega as follows. So until the first time at which one of the clock rings, so recall that tau1, I had ordered the clock rings in increasing order, and tau1 is the first time at which one clock rings, and up to that time, the configuration equals the initial configuration. At that time, so at time t1, I look at which is the site on which the clock rings, say it is site X, and so it's k is equal to 1 here because it's the first site, the first time that it rings. And the first thing that I check whether the this function is equal to 1, namely if the constraint is satisfied. If it is the case, I replace the current configuration with the configuration in which if the variable, the coin toss at that time is 0, I empty that site, the site X. If the coin toss is 1, I fill the site. So B is the map Bx 0 or 1 is the map in which I fill or empty, I empty or fill respectively the site X. And this variable Bk1 is, as you might see from the previous slide, sorry, there is all this writing, is the coin toss that is associated to the ring at that site. So it's the variable that is telling me whether I'm putting a 0 or a 1 at that site. Okay, so accordingly, I update. If instead the constraint is not satisfied, so if this function is 0, I don't update and I keep the same configuration, the one that I had at the beginning. And I proceed iteratively. I go to the next clock ring. Up to that time, I preserve the same configuration. Then at Tau2, I check which site has the clock that rings. If the constraint is satisfied, I update it depending on its, by setting a new variable, which is dictated by the coin toss at that time on that site, etc., etc. Okay, so I needed this proper definition in order for future use, which is a little bit boring, I guess, for most of you. So, okay, so this graphical construction gives a Markov process on the space of Cadillac function on this finite volume with initial condition eta, and this corresponds to the informal definition which I gave at the beginning. So it's our KCM. Sometimes we call this KCM a UKCM if I want to stress that it depends on the update family U that defines the constraint. I call P of eta and A of eta the law of this process started from configuration, the law and the expectation of this process started from eta, and I call by P eta the corresponding semigroup of the Markov process and L the corresponding infinitesimal generator. So the action of the generator, if you go back to the definition, it's not difficult to see that the generator acts on local function as the sum on all sides of the function Cx, which encodes the rate, times the mean of the function at site x with all the other variables held fixed, minus f of eta, which can also be rephrased in the following way. Okay, I can the second way I'm rephrasing. So sorry, usually one is at the backboard, so I'm writing very slowly as you are. So if I'm going too fast, please tell me. If I'm going too slowly, please tell me.
Cristina.
Yes.
So sorry. So in your notation, you have remove omega from C.
Yes.
So the
yes, I removed I dropped omega, so the boundary condition, because it was too heavy, and also because I'm going to say in a second that the construction can be extended to infinite volume, and that's what I'm mostly interested in.
So in these definitions, omega is understood. So it's fixed
yes,
once for all. Okay.
By the way, do you see my mouse when I move around or not?
Yeah, yes.
Okay, when I point. Okay,
yes, I do not know. Okay, I am in the first row, so with the new glasses. So.
Okay.
Glasses.
Yes, that's very important. Okay. so here
okay,
there is an omega in the constraint, because the constraint is looking in a neighborhood. If I am on the boundary, the neighborhood is also outside. So it's understood that this function which encodes the constraint contains the boundary configuration.
Cristina, may I ask a question?
Yes, Milton.
Yeah, so in this definition that you're using mu x of f there in the generator, right? So that means that in principle, this definition also can be extended to Glauber dynamics of any of your favorite measure on the space of configurations.
It's just that then things become more complicated. Yes, you can take another Glauber. Yeah, in fact, you can consider the same models in which you have the constraints. If I have this Cx, but on top of that, you also have an interaction. Yes, it can be another measure.
And that will give you also a reversible dynamics with respect to the measure mu that you're using there.
Yeah, because I would say yes. Yeah, because if because you're building it like that, you take your favorite Gibbs measure, and because Cx here does not depend on eta at site x, so Cx of eta and Cx of eta flipped at x are equal.
There was a question in the chat. Can you recall the definition of Cx of eta, please?
Yes, Cx of eta is here. Yeah, a big blackboard with everything written and not raised all the time would be much better. So Cx of Eta is a function which equals 1 or 0. It equals 1 if, let me say it in words, if the constraint that you have chosen to construct your KCM is satisfied. For example, if you are choosing FA to F model, this Cx equal 1 if at least 2 empty neighbors are, if there are at least 2 empty nearest neighbors. In the general framework, Cx is equal to 1 in configuration sigma if there exists at least one set in your update family, such that the configuration is equal to 0 on all the sides of this set in the update family translated at X. So this corresponds, but let's look at the generator and see whether you agree that this corresponds to the dynamics that I announced informally at the beginning. So which is the change in a configuration? So this the action of the generator corresponds is the derivative of the at 0 of the action of the semigroup. So how can I change a configuration? So this, so if you recall what I said about the dynamics, I said that on each side there is a Poisson clock of an exponential clock of mean time 1, and when the clock rings, if the constraint is satisfied, I do something, and if it is not satisfied, I do nothing. So first of all, this Cx, which is in front here, is either 1 or 0. 0 when the constraint is not satisfied, it corresponds I do nothing, meaning there is no change in my configuration, in my configuration corresponding to this clock ring. Okay, so Cx equal to 0 corresponds to the case in which the constraint is not satisfied. Instead, Cx equal to 1. So this is just the control variable. Let's say Cx is equal to 1 when the constraint that you have chosen is satisfied by the current configuration. And if it is the case, why the action is mu x of f minus f of eta. So this is the action. I mean, this is subtracting what was before. So why this mu x of f? Because I'm saying that I'm throwing away the occupation variable that I had before on that side, and I'm replacing it with a fresh variable, which is chosen according to one with which is 1 with probability 1 minus q and 0 with probability q. But this corresponds to choosing it according to the restriction on that side of the Bernoulli measure. Okay, it's the same thing of saying that I'm for the configuration at site X, when the clock ring at X and the constraint is 1, so the constraint is satisfied, so that this function is 1, I'm taking a fresh variable at equilibrium. Equilibrium is mu is the product measure at density Q. X here indicates that I'm making the mean only on X. Okay. And it's the same thing as writing this is a simple algebra. And I wanted to write it like this also because people which are familiar with the Glauber dynamics perhaps are more familiar with this language. Just writing that that I'm making a flip at site X. So if I have the configuration eta, I change it to the configuration eta updated at site X. So change it at site X. And in front, I have the part of the rate which depends on whether the site that I'm changing was occupied. Or then I change if it was occupied. Sorry, here if it was occupied, so eta x was 1. I'm changing with probability q. So I'm setting to 0 with probability q. If it said it was empty, so this first term means non-zero. Then I'm changing to occupied with probability 1 minus q. I hope it's clear, but if it's not, just tell me. I'm not seeing the chat. Okay, so then, as I was saying that, so I needed to make the graphical construction because we will need it later on, but just on finite volume. But we will be dealing most of the time with the models in infinite volume. But then it's the standard argument for interactive particle systems by using the fact that the constraints are uniformly bounded. These functions are just 0 and 1, and are of finite range. It was important to say that the family, the update family, so these sets that determine whether the constraint is satisfied or not, you can choose them as you wish, but they should be of finite range. So using this fact plus a percolation argument is standard to extend this graphical construction, so this construction to infinite volume, to construct the infinite volume process. And also notice that, as usual, the graphical construction provides a natural way of coupling processes started from different initial configurations, in the sense that I can consider two initial configurations and let them evolve on the same space with the same realization of the coin tosses, so this variable, Bernoulli variable that determines whether I update to 0 or 1, and of the clock rings. The point, which goes back to what I was saying initially, is that this coupling and no other coupling, in fact, preserves the partial order among configuration. In the sense that if I take two configurations which are partially ordered in the usual sense, in the sense that sigma is smaller than sigma prime, if for every site in which sigma is equal to 0, also sigma prime is 0, though the constraints are monotone, because you see that the more I add empty sites, if the constraint is satisfied on a configuration sigma prime, and I add more, I've written in the wrong sense. Okay, so if I'm adding more empty sites, so if the configuration is smaller, the constraint is deterministically, if it was already satisfied with less empty sites, it will be satisfied again. So this sense here is in the converse. So the constraint function is bigger on the smaller configuration. Despite this monotonicity correlates, the process itself, this coupling does not preserve this partial order among configuration, and it's due to the fact that having more empty sites can induce validating, so making possible some of the updates which were putting more occupied sites. And this corresponds to the fact that if I have two initial distribution from which I start the process, two processes, these initial distribution are partially ordered. This partial order is not preserved later on by the dynamics. Okay. Okay. So super slowly. So now using the formula for the generator, and using the fact that the constraint at site X does not depend on the configuration at site X, so the fact that sigma is equal this function on sigma and sigma flipped at X, and using the product form of mu, it's easy to see that the generator is self-adjoint in L2 of mu, meaning that for any two function in L2 of mu, the mean of the first function times the generator applied to the second function is also equal to the mean of the second function times the generator applied to the first function. Okay, and this coincides with the fact, so the fact that so first of all the process is stationary if I start it from the measure mu, but more than that, the law of the forward and backward trajectory are equal. So the process is reversible if I start from the invariant measure mu. Okay. So now the next natural question is whether the process is ergodic in the sense of interactive particle system, namely if this measure mu is the unique invariant measure, and if I converge to that starting from an initial distribution. And the answer is no, and you already know that because I told you that there are configurations that are blocked, and also measures which are concentrated on this configuration are invariant. And this set of invariant measures will depend on the choice of the constraints. Okay, so before discussing more what happens when I start for the stationary process, so I know that I don't converge to the equilibrium measure starting from any initial distribution, but the other natural question is what happens when I start at equilibrium? Do I have, does the process converge to equilibrium in L2, at which speed, etc.? Before doing that, I would like to make this small interlude in which I will give you the formula for the Dirichlet form, for the quadratic form, which will positive form, which will be a very important tool in our analysis. So the Dirichlet form is simply defined. So from an analytical point of view, is simply the Dirichlet form of a function f is simply minus mu, the mean of the function times the generator applied to the same function. And using the formula of the generator, in this case, the Dirichlet form, which is a positive, it's always bigger or equal to 0 for any function. Using the formula of the generator, it can be easily seen that it can be rewritten into equivalent form, which will be both very useful for us. So one is by writing it as the sum over all sides of the mean on the whole Bernoulli measure of the constraint on site on the given site times the local variance on that site, which is, as we said, a variable which a function which depends on all the other variable outside X. Or this Dirichlet form can be equivalently written as a sum over all sides of the mean of the rate function times a function which contains the rates of the Bernoulli measure. Here there is a parenthesis which is missing. So is 1 minus eta x times 1 minus q. Times the square of the difference of the function modified at x minus the function evaluated on the configuration modified at x minus the configuration, the function evaluated at the original configuration. Okay, so this is the Dirichlet form, play an important role. So I wanted to give the formula now. So I mentioned several times that there are, depending on the constraints, there may be different blockhead configurations, and also with the example of FA to F of this double row that can be blocked forever under the dynamics if it is completely occupied. You also understand that there can be configuration which contain blockhead clusters. So I want now to give you a simple deterministic algorithm, which to identify these blockhead clusters that configuration might contain. So you fix your favorite KCM, so you have chosen the constraint, and now you pick a configuration eta, and you want to know whether this configuration contains a subset of sites which are occupied and forever blocked under the dynamics, as it is the case for the double bar of the FA2F model. In order to do that, you simply have to apply a deterministic algorithm, which is the following. You pick your initial configuration eta, and then you apply to eta the following map, the map T, which empties all the sites in which the constraint is satisfied. So on site X, you put 0 if the constraint is satisfied, or preserves the existing configuration if the constraint is not satisfied. So this map is a monotone map, which is also known as Bootstrap Percolation Map. So this is the link with the Bootstrap Percolation, which is coming. And it's monotone because you see, I can only empty sites via this map. I cannot fill them. If a site is filled, it can be empty if the constraint is satisfied. If it is already empty, it stays empty because I can never fill sites which are empty. And then I can apply iteratively this map. So I applied the map, the Bootstrap map, and then I reapply the Bootstrap map of the obtained configuration, and so on and so forth. And until reaching either a configuration which is completely empty, or until reaching a configuration which contains a backbone of sites which are occupied, but which can never be emptied because they are mutually blocked by the constraints. Okay. And now the key observation, the key easy observation is that if I denote for a given configuration eta by B of eta, the backbone, so the set of sites which are forever, which remain occupied at the end of infinite iteration of the Bootstrap Percolation Map, then if I consider my KCM, my stochastic dynamics, started from the same configuration, all the sites of this backbone remain forever occupied, can never be emptied. And furthermore, if at any later time I take the configuration on which I have evolved and I check which is the backbone of this configuration, it's always unchanged, which means that there is the double due to the, which is trivial if one thinks about on reversibility, but sometimes it's not so evident at first sight. So if I have a configuration that contains a backbone which remains under infinite iteration of the Bootstrap map, not only this backbone is forever occupied under the stochastic dynamics starting from the same initial configuration, but also this backbone is invariant under the dynamics. The sense that I can, in particular, if I don't have a blocked cluster of particles, initially I cannot create it, okay? Which is trivial due to the reversibility, but sometimes it's natural to think whether this sort of a blocked cluster can be created from nowhere. It's not possible. Okay, notice also that once one, depending on the constraints, one explores the different possible backbones of the different configuration, it's easy to construct invariant measures which are different from the measure which is concentrated to the completely filled configuration and different from the Bernoulli product measure. In fact, any measure which is, if I have a configuration which has a backbone of blocked particles under the Bootstrap map, and I take a measure which is 1 over completely occupied, so on this backbone, and product with the density y minus q otherwise elsewhere, this is an invariant measure. So there is a whole multiplicity of invariant measures. Okay. So now, I told you that first day is setting all the tools. So I need yet another simple tool, which is connected with this notion of, is again connected with this notion of Bootstrap percolation in some way. It's the notion of legal paths, the notion of possible paths connecting two configurations. So if I have two configurations in my configuration space, I will say that they are connected one to the other by a legal path gamma. If the following holds, if gamma is a sequence of configuration, okay, gamma is a sequence omega 0, omega 1, omega 2, omega n configuration, such that the first configuration is, I'm sorry, I wrote omega, but it's eta. The first configuration is eta, the last configuration is sigma. So I take this sequence of configuration. The first one should be my initial configuration, the last one should be my final configuration. And in the middle, all this sequence of configuration should be such that the configuration at step I here in this sequence of configuration is obtained from configuration at step I minus 1 by flipping a single site on which the constraint is satisfied. Okay, so it's a very natural notion. So I have there are configuration. Consider, for example, a configuration for the 1F model in which I need just one empty site in order to perform a move. And suppose I start from a configuration which contains a single empty site somewhere. So eta is a configuration which contains a single empty site. Sigma is a configuration which contains a single empty site, but somewhere else. Okay. So these two configurations are actually connected by a legal path in the sense that starting from the initial empty sites, I can empty one site nearby, then fill the site below because my constraint is just asking to have at least one empty nearest neighbor, and continue until reaching the site which I want to empty in order to construct the final configuration. Okay. But for example, if I start from a configuration which is which contains a single empty site and I I'm looking at the 2F constraint. From that configuration, I can reach nothing else. There is no legal path to any other configuration because all the constraints are not satisfied. Okay. So a very simple observation is the following. If I have a configuration and I pick a site in that configuration which is not contained in the backbone of this configuration, namely, I pick a site and I pick a configuration such that if I apply on it the infinite iteration of the Bootstrap map, at the end, this site will be emptied. Necessarily, there exists a legal path, so a path of allowed configuration changes allowed by the constraints of my dynamics, which brings me from the initial configuration to a final configuration in which the chosen site has been emptied. So I indicate by eta x0 the configuration in which I have emptied the site x. Furthermore, if I'm picking a configuration eta such that the site x does not belong to the backbone of this configuration, this means that if I apply the Bootstrap map a sufficient number of times, I will be able to empty this site. So this means that there will be an index n sufficiently large, so that if I apply the Bootstrap map n times, at a certain moment, this site will be emptied. Okay, so if this is if now I take a configuration which belongs to the subset of configuration which are emptied after n step of the Bootstrap map, this implies that from that configuration I can reach via a path of moves which are allowed by the constraints and which has a length, which is a certain length, which is will be upper bounded by a constant which depends on n and will involve only sites which are in a certain boundary of the initial site, which is able to empty my site x. So I realized that here a drawing would have been more illuminating, but unfortunately I'm not on a tablet in this moment. So there is nothing difficult in this and nothing sophisticated in this notion. Is just saying that whenever I know that a site does not belong to the backbone of site that will remain until applying infinite time as much as I want this Bootstrap Percolation Map, for sure this site can be emptied by that map, okay, by that iteration of the map. And this also implies that there is a possible path which connects my configuration to a configuration which only differs on that site by emptying it, or it differs because I have emptied that site. Okay, if the site was already emptied, I have to do nothing. If the site was not empty, I just perform the Bootstrap map until step n. All the moves of the Bootstrap map. The Bootstrap map occur, let's say, in parallel. So it empties all the sites which have the constraint satisfied. It's not a problem for me. I have a dynamics in which I have to empty one site at a time. I can empty one site at a time, those which have the constraint satisfied, and do all that the Bootstrap map has done until the iteration n in which it has emptied site x. And then I leave that site empty and I rewind. So I redo in the reverse all the moves in order to refill all the sites that I had emptied, because I want to reach a configuration in which I have only emptied a given site, the one which did not belong to the backbone. And I can rewind because with the legal path, because as I said, if the configuration that I'm looking at has more empty sites, it is the case because I'm leaving an empty site at x, the constraint is even more satisfied because I'm leaving an empty site somewhere. So by rewinding, I will find constraints which were satisfied when coming to that site and now are even more satisfied because I'm leaving an empty site behind. Okay, I'll do, if it's not clear, I'll do a drawing for tomorrow. So now that we have all, we're equipped with all the notions, I'm ready to address the issues that I want to look at. So the first issue is what happens if we evolve the process starting from the equilibrium measure. So first issue is, does the process mix if we start from the equilibrium measure? Meaning, do we decorrelate in the physics language? Do we decorrelate? So if I take two functions, f and g, if I take the infinite time limit of the mean over the stationary process of the function f times the function g evaluated at the evoluted configuration, does this mean decorrelate? Does it converge to the mean of f times the mean of g? Second question, if of course, if mixing occurs, how fast does it occur? And second question, if mixing occurs, does a stronger notion of the stronger property of convergence to equilibrium in L2 also occurs, where convergence in L2 means that for any function in L2, the infinite time limit of the function obtained by applying the semigroup to the function f, does it converge to in L2 to the mean of f? So what we will prove is that, so we will answer to this question. We will prove that depending on the choice of the update family U, which defines the model, there exists a critical density, which belongs to the interval 0, 1, such that when the density of, when the value Q, which is the parameter that determines the density of empty sites in the equilibrium measure, is larger than this critical density, converges in L2 and therefore also mixing occurs. And when the Q is smaller than this critical density, there is no mixing and therefore not even convergence. So there is a critical density which separates the regime in which there is convergence and mixing and the other regime. And we will see that depending on the model, at the criticality, both behavior can occur. And furthermore, what is most important, we will be able to tackle the speed of convergence to equilibrium in the mixing regime. We will prove that when Q is bigger than the critical density, so in the mixing regime, convergence to equilibrium occurs exponentially. So in this, the mixing occurs exponentially fast. And we will then study the speed of convergence in this exponential mixing. So now what can we say on this critical density? So first of all, this critical density is very much, so it's connected to this underlying Bootstrap Percolation process. So this algorithm that I just defined to identify the blocked clusters, in fact, plays a very major role, because the critical density at which the transition between the converging and mixing regime and the non-mixing regime occurs is also a critical density for this percolation process, Bootstrap percolation process. So let me define this density. So suppose that I consider the following process, start from the deterministic process, start from the equilibrium measure, mu, and then apply iteratively n times the Bootstrap map, the map that in parallel empties all the sites which are have the constraint satisfied. Since this process is monotone, because we just empty sites, there exists by monotonicity a limit as n tends to infinity of this measure obtained by iterating n times. And there is a critical density which separates the regime in which on this limit measure, the probability that a chosen site, say the origin, is empty is equal to 1, or it is smaller than 1. So, first of all, okay, this process is monotone. So it's clear that if at a certain value of Q, which enters in this initial distribution, at the end of the iteration, the origin is empty with probability 1. Necessarily, it is empty with probability 1 also for higher choices of Q. So it's really a critical density separating the two regimes. And also, this critical density corresponds to the value at which backbones starts to arise. So when Q is larger than this critical density, there are no backbones in the configuration. So with probability 1, the origin does not belong to the backbone. When Q is smaller than this critical density, the origin belongs with probability larger than 0 to this backbone. So it's really a percolation threshold for the bootstrap percolation dynamic. And what I was saying is that the critical density separating the mixing and non-mixing regime, and also convergence and non-convergence regime for the KCM, coincides with the critical density for the bootstrap percolation. And it's quite simple. In fact, this is quite a simple result, which how much? Okay, so just to give you a flavor of the first proof. So why is this critical density the same as the one for the bootstrap process? So first of all, suppose when we are for density of the density of our dynamics, or the value of Q in our dynamics is smaller than the critical density of the bootstrap percolation. Then I can easily show that there is no mixing with the following choice of the two functions, which I can show that for which I can show that the mean of the function g up times the function f evoluted at time t does not converge to the product of the means. You can take as a function f the function which is the indicator function that the origin belongs to the backbone, and as a function g the indicator function that the origin does not belong to the backbone. Okay, then for sure the mean of f times g is 0. The probability that G doesn't that the origin does not belong to the backbone is bigger than the probability that the origin is 0, so it's bigger than Q. And since we are in the regime in which blocked clusters percolate, and so the origin belongs to the backbone with probability which is larger than 0, mu of f is bigger than 0. So for sure, and furthermore, last but not least, as we said, the backbones are left invariant by the dynamics. So if the function f does not evolve under the dynamics, so this product is equal to mu of g times f, which is 0 and which is different from mu of g times mu of f. So you see that once there is percolation of blocked clusters, there cannot be convergence, there cannot be mixing. And conversely, in order to prove that when the density Q is larger than the critical density for bootstrap percolation, which we have convergence in L2 to equilibrium, one has to recall the fact that convergence in L2 is equivalent to the fact that the only functions which are eigen functions which with the eigenvalue 0 of the generator are constant. So perhaps I can just leave you with this. If we have to close, I can just leave you with this first page and say that in order to prove this the fact that 0 is the only functions which are left invariant by the dynamics are constant almost surely in this regime, so that we have convergence in L2. you will have to use the fact that, so I'm giving here the ingredients, so, and then tomorrow I go faster on the slide. So you'll have to use the fact that thanks to the fact, so you want to prove that the fact that LF is equal to 0 implies that F is constant. So the variance of F is 0. So you will have to use these two things. So first of all, the fact that you can upper bound the variance of a function as a sum of over all sides of the mean of the function, or mean of the local variance of the function over all sides. And then you will have to use and then you want to prove that this right-hand side is upper bounded by 0 whenever I know that the generator applied to F is equal to 0. Okay, so that F is a constant. So now it's the moment to use the fact that you know how you write the Dirichlet form, because we wrote it before. So the Dirichlet form, which is mu of F mu of F LF is equal to 0 also, because LF is equal to 0, and it's written in this form. So you see, it's very much similar to this one. So it's a sum over all sides of the mean of the local variances. The only difference is that here I have Cx. Cx is a function which is equal to 1 and 0, so I cannot upper bound this right-hand side here with this Dirichlet variance, Dirichlet form, and say that the fact that it is 0, this implies that the variance is 0. So we'll have to, it's here that you will have to use what I said before. So the occurrence of the fact that I can we are at a density of sites, empty sites, which is bigger than the critical density of Bootstrap percolation. So with probability 1, we know that each site does not belong to the backbone. So we have to use the fact that each site is emptiable by a legal path, the legal path that I announced before, this path of on configuration space, which is in which all the changes are allowed by the dynamics. So I think I will stop here.
Brilliant. Yes, please.
Yeah.
Thank you very much, Cristina.
Oh, 37, sorry.
Yeah, maybe have time for some quick questions. Thank you very much. If you have questions online, then maybe you can unmute yourself. If you can't, then let us know in the conversation. Someone will keep an eye out. Okay, thanks. Questions from the room? Can you unmute yourself in the...
Yeah. Cristina, I have a question about the slide on the mean time to empty at the origin. So you have these different models.
Yes.
And the one which I'm a little confused by is the last one. So you have the exponential to the log of q squared over q to the 4th, right? So because q is between 0 and 1, so log of q to the 4th, I think, is negative. So does that make sense? Because
for the Duarte model, there is an exponential of positive constants
yes,
q to the 2 times the logarithm. So okay, modulus to the power 4. So what's the question?
So my question is the log of the q to the 4th, right? So that's a negative number.
Ah, no, sorry, but sorry. A parent was missing.
Ah, okay. So it's the.
If you ask like that.
Okay, I saw the chat.
The parent was missing. So sorry.
Okay, makes sense now. Okay, thank you.